All right, so now in the last video we learned about systems of linear equations and how to solve them, and I think I talked about setting it into row echelon form, a system of equations, and then working backwards to find the solution. So as a reminder of what row echelon form is, it's pretty nice. This is example one. This is a completely different matrix, or system of a linear equation I'm about to write, but so x, let's say we had x minus y plus 3, z equals 4, and then y plus, let's say 9z equals 2, and then z equals 5. All right, that's a little bit big. Let's say z equals -1. This is row echelon form because, and I guess the definition of row echelon form is basically you have like almost one less variable in each row, right? The first equation has all three of our variables. The second equation doesn't have the first, right? So it only it doesn't have the first, and the third doesn't have the first two. Maybe they do, but it's like 0x, right? And 0x, 0y. And the other sort of definition is that the first sort of variable, the leading coefficient is 1. So we have an x here, that's kind of our first variable, and the leading coefficient is 1. Y is kind of our first variable here, its leading coefficient is 1. And then z, the leading coefficient is 1. And the reason why row echelon form is really nice, this is a pretty easy system to solve because, hey, you could just say, you could work backwards. This is called back substitution, right? You could say, okay, plug it back in here, y minus 9 equals 2, that would make y 11, and then I get minus 11 minus 3, that's minus 14, so I think x equals 18. Like, you can solve the system of equations by just plugging everything in backwards, right? You solve for y, and then you can solve for x. Now, reduced row echelon form, for this same system of equations, I'm not going to alter this, reduced row echelon form would kind of look like this. Was that an 11 or a 9? I think that was an 11. So obviously you see this and you're like, this is just a solution set, right? What do you mean reduced row echelon form? It's gonna make more sense in a second, but the way you kind of have to imagine this is like so. So x plus 0y, and then we're gonna have plus 0z, right? 0x plus y plus 0z. And then 0y plus 0x. So it's the same deal as, sort of the same deal as row echelon form. This is reduced because now there's zeros, right? So you have x, 0, 0. So basically, if you have a leading coefficient 1, everything above and below it, if you think about like this equation, zeros, right? Everything above and below zeros. I think above and below zeros. If you get a system of equations in reduced row echelon form, you already kind of know the solution set. So we're going to talk about how you can get systems of equations into reduced echelon form and row echelon form using something called Gaussian elimination and then Gauss-Jordan elimination. So I'm going to teach you these two methods, and I'm going to teach them hopefully so that you're not memorizing a bunch of steps, but you can see how logically these methods actually make sense and how it's pretty almost logical and intuitive, and you could probably even figure it out on your own if you know the definition of row echelon form. So to solve this system, you can solve this, just using like this. What we're going to do from now on is start using augmented matrices. An augmented matrix, so a matrix is just a way to store information. It stores numbers in rows and columns, and I'm going to show you use these brackets to show that it's a matrix. And then the way you store the numbers is, let's say you have rows and columns. So there are 3 equations, so we're gonna have 3 rows. And there are really, each variable, x, y, and z, has its coefficients, and then there are these constants. So we're gonna use 4 columns to represent that, right? So 2, 3, 3, 3. This represents the x coefficient. the y coefficient, the z coefficient, and the constant equaling to 3. So what's nice about this is what's nice about this is that you don't have to write x, y, and z a bunch of times. What's not nice about it initially is you kind of have to get used to working with a matrix, right? You're not used to seeing the z's and the x's and the y's, so it takes a little bit of practice, but it's akin to, like, I don't know, what's something that, like, is initially hard to learn, but then you just do it all the time because it's so much, like tying your shoes. I don't know, it's like you could use Velcro, right? But once you tie your shoes, it's just I don't even know if that's a good analogy. But let's just try to solve this system using Gauss-Jordan elimination. Gaussian elimination. So Gauss, his idea is like, I want to get into, and he's a mathematician scientist, I want to get this into row echelon form. So I need to have zeros, right? If you think about this, these two numbers need to eventually become zeros. This needs to become 0, right? So I have these 3 zeros, and then each of these, right? Because this represents our x leading coefficient, y leading coefficient, z leading coefficient. These need to eventually be 1. So you could start off by, hey, let's get a 1 on top, right? Divide this by 2, so I get a 1. Divide everything else by 2 so that it's the same system. But that'd be really annoying to work with. We're gonna be working with 1.5s and 3 half. No, let's not do that right now. We can do that at the very end. What we can do right now is reduce everything else. So the first step you can imagine, if you think about, well, how would you solve this system of equations just like this? Well, you could pretty intuitively tell, hey, let's multiply. I want to get rid of this 6x. So what if I added negative 6 to that, right? So what we can do is we can add negative 6x, right? So negative 6x, multiply the top equation by negative 3 and then add. So 6, right? When I get multiplied by negative 3, I get negative 6. So when I add those, this one will become 0. So I'm going to do the same thing, but just in this augmented matrix form. And by the way, augmented matrices, they sometimes have a line to separate the equation from the coefficients, or constants. So let's multiply this top row by negative 3. So I'm just going to write them here as a way to bookkeep. So negative 6, negative 9, negative 9, negative 9. So when I multiply this top row by negative 3, I'm going to get these constants. So now I'm going to add them to the second row. So that becomes 0. Negative 9, that becomes negative 3. That becomes negative 9 plus 12. That becomes positive 3. And then this becomes 4. And what I'm going to do is I'm going to write the row reducing step, the row reduction step that I just did. So what I just did is I took row 2, which I'm going to denote with R2. I took row 2 and I subtracted it from 3 times row 1. Or you could say I added it with negative 3 times row 1. And that becomes my new row 2. So the idea of this is like, hey, you could give someone just this and they will be able to perform this step, right? It's just kind of a way to bookkeep what you're doing. And they might ask you to do that on a test. So now we're going to do the same thing. I want to get rid of this 12 so that this becomes a 0. So I'm going to multiply the top by, hope that you can kind of tell, negative 6, right? Because when I multiply this top equation by negative 6 and then add them, I'm going to get a 12x minus 12x after multiplying by negative 6. That's the idea. My goal is to do, this row echelon form where these first, this first column, the bottom 2 rows, I guess, are 0, right? So 2, 0, 0. So if I bookkeep this, I'm going to have negative 12 when I multiply this by negative 6, negative 18, negative 18, negative 18, right? When I multiply each of these by negative 6. I'm going to start adding them. So negative 12 plus 12 is 0. 9 minus 18 is negative 9. Negative 1 minus 18 is negative 19, which is a little ugly, but it's okay. 2 minus 18 is negative 16. Okay, so now the row reducing step here is, or row reduction step is going to be R3 minus 6R1 is R2. All right. So the next sort of step is now, to get this in row echelon form, is, well, I'm going to have to make this number 0, right? And remember, in order to be truly row echelon form, this 2, this -3, and this -19, those are going to have to end up being 1 eventually, right? Like this coefficient, that coefficient. We'll do that at the very end, because that's a very simple thing to do to get the fraction. But right now, let's work with whole numbers. So if I go, let's just go over here, use some of the space here. So I'm going to have 2, 3, 3, 3, 0. So -3, 3, 4. Now, here's the deal. If I want to get rid of this -9, you might think, hey, I have a +3 here. It's going to be a little bit easier to just multiply this top row by 3 and then add, because I don't want to work with the negative. But you notice that, hey, I have a 2 over here. So any operation I do to the first row and then add it over, this little 0 over here is not going to be 0 anymore. I'm going to be adding a 2 or a 6, right? So logically, that's probably not a good idea, because I'm just going to have to work backwards. I'm kind of undoing what I just did. So instead, I'm kind of left with really no choice but to use the second row, because the second row has this 0. There are 2 zeros here. I can throw whatever operation I want at this 0, and I'm not going to, it's not going to change that 0. Anything times 0 plus 0, right? It's going to be okay if I make alterations to the second row and add it over. And in this case, it is still kind of nice, but sometimes you get nastier stuff. Like, imagine if this was a 5, right? Well, you have a choice. It's best to just work with this, and do it like that. I think that's just more simple. Working, you don't want to undo stuff. So let's do that, right? I'm going to multiply this stuff by -3, so I get a 9, and that +9 is going to cancel out that -9. So if I write the coefficients, and you don't have to do this at each time, you can kind of do this in your head, but while we're still starting, right, those are the coefficients. So if I add 9 to -9, I get 0. -9 to -19, I'm going to get -20, -20, I'm not sure, -20, why am I blanking? 28? 19 plus 9, yeah, I think -28. -12 minus 16, I'm going to get 28 as well. It's pretty nice. All right. So you can kind of tell we're pretty much done here, right? So I'm going to say R3, I did R3 minus 3 times R2, right? Because I multiplied everything by -3. That gives us R3. Now, you could actually leave it here, right? You could write this, you could write row reduction steps, and you could say, okay, I'm going to make these 1, right? Because -28, I could just divide everything by -28. I get 1 here, and then I'm going to divide by -3. So I get 1, -1, and then -4/3. And then I can divide everything by 2 here. So I'm going to get 1 and then a bunch of 3/2. And that's Gaussian substitution for you. And now you can kind of tell, oh, if this is z, this represents z. So 1 times z equals 1. Z is equal to 1. And you can kind of work backwards and get everything else you need. What I'm going to do is I'm going to show you Gauss-Jordan elimination. Gauss-Jordan elimination is really the same thing. Not really, but it gets systems into reduced row echelon form. And the way you do that, right, to do reduced row echelon form, well, I'm going to need I need this to be 0, this to be 0, this to be 0. So I just have this line of 1s and 0s all around. And what you can imagine, you kind of have to go backward, because I already have this 0, 1. So once again, any operation I do here and add it over, I'm messing up this 0, 1 that I need for reduced row echelon. But if I work backwards, which you can kind of, it's going to be easier anyways, but if I work backwards, this 0 ain't doing anything to the 0 and the 1. So it's pretty nice if you do that. Row echelon form is great. It's one of my favorite things. Let's go ahead and make this reduced row echelon form. So I have a 0, 0, 1, 1. If I add the 1 over, so 1 minus 1 is 0, which I wanted. And then I'm going to have to do 1 minus 1/3, which is negative 1/3. 1 minus 4/3 is negative 1/3. All right. So now, I want to do reduced row echelon form again, and I'm just going to use this bottom one. Or no, I'm going to use this one. Or I guess it doesn't matter. I can start by using this one, eliminate, this one, eliminate, right? I should write the row reduction step. I did R3 plus R2 is now row 2. So now, I want to get rid of this 3/2 and that 3/2. So I'm going to work backwards again. I'll use the bottom row, and I'm going to be multiplying everything by 2/3. Or no, 3/2, yeah, obviously. I'm going to be multiplying by negative 3/2, so I'm going to get a 0 here. And then I'm going to have 3/2, right? I'm going to have 3/2, negative 3/2 here, so then I get 0 here. And just for the sake of making this a little bit quick, I'm not going to write the row reduction steps. But now, then I'm going to have, I just need to get rid of that 3/2. So I'm going to multiply by negative 3/2. I get 1, 0, 0. Negative 3/2, 0, 1, 0, 0. Oh, did I write a 0? This should be negative 1/3. That's one thing about these matrices. You can sometimes miss that kind of stuff. And then I get 0, 0, 1, 1. That's reduced row echelon form. And you can pretty clearly tell the answer. This x is going to be negative 3/2. This y is going to be negative 1/3. And this one is going to be 1. And let me just verify that. So if I pick, I think that should work out. Hopefully it works out. Maybe I made a mistake in the comments. But there you go. That's the solution set. I'm just going to write it so I know to check it. It was negative 3/2. Negative 1/3, 1, something like that. Okay, so now let's do the second one. Let's solve this system of equations. x1 minus 2x2 minus 8x3 is equal to 0. 3x1 plus 2x2 is equal to 0. You should already have an answer. You should already have a little bit of an answer here. The one answer is 0, 0, 0. Hey, there we go. That wasn't too bad because we have these two zeros here, right? So if I plug 0, 0, 0, 0 here, obviously we'll get 0. Obviously. Trivially we'll get 0. This is what we call a trivial solution. So this system of equation is special because its constants are equal to 0. So each of the equations are just equal to 0. So we call this a homogeneous system. I'm not sure why it's called homogeneous, but I'm sure it has some maybe connection. Homogeneous means same, so I don't know what's so same. I guess it's just, I don't know, same, I don't know. I don't know. But the trivial solution, you can always get a trivial solution, which is going to be 0, 0, 0. So that is the deal. Yes, you can always get 0, 0, 0. What we're going to try to do is we're going to try to find a non-trivial solution. What are some more solutions to this than just 0, 0, 0? Are there any more than one solution? We'll see. So if let's just make this into a matrix. So we should get 1, negative 2, negative 8, 0, 3, 2, 0, 0. So what you notice is you have fewer equations than variables. That means we should really be having an infinite solution of systems or equations, right? But there are, if you imagine two planes, because these are just equations of planes. So if you imagine two planes crossing, when they cross, they form a line. And that line is the solution to this system of equations. So in that case, in that case, we can find the sort of I don't know what you call it, line, but the parameterization of that line. So let's try to head and do that. And what we're going to do is we're going to get this into reduced row echelon form with like, so when you're working with fewer equations than variables, your reduced row echelon form is going to be like, this is 1, 0, and then 0, 1. Like usually it's 1, 0, 0, 0, 1, 0. But because that's impossible to get, I hope you can kind of realize, because if you have 1, 0, 0 constant, 0, 1, 0, 0 constant, that means there is a solution which just won't work. So reduced row echelon form is going to be a little bit different. But I'm going to show you why we're doing reduced row echelon form. So let's just do reduced row echelon form. Get this out of here by doing a -3. So -2, -8, 0. So I want to multiply the top by -3. I'm not going to write the steps, but it's good practice if you want to try. Multiply the top by -3, add it over, so I'm going to get 0. -3 times -2 is 6, so 6 plus 2 is 8. And then I'm going to have positive 24. I'm going to have 0 still. Okay? So now I'm going to have, I want to get rid of this. I want to make this first of all like a, like a 1. So that this is row echelon form. That's pretty easy. Divided by 8, I get 1, 3, 0. And then I'm going to get rid of this -2 by just multiplying the top by 2. And if I multiply the top by 2, I'm going to have a 0. So, 2 plus 2 minus 2 is 0. 6 minus 8 is -2, 0. And then 0, 1, 3, 0. So the reason I'm doing reduced row echelon form is because what I can do now is say, well, I know if I write this equation, I get x minus 2z equals 0, and then y plus 3z equals 0. What I can do is I can say, hey, let z equal t, where t is just some real number. Or maybe, I don't know, it could be non-real. I don't know. I don't think. Just say all real numbers. So I get x minus 2z equals 0, x equals 2z, or 2t, y equals negative 3t, right, when I multiply the negative 3z over, and I get z equals t. So this right here is the line, the parameterized line that gives me all these sort of equations and whatnot, or all the sort of points that are at the intersection there. So it's pretty nice. This reduced row echelon form, it's pretty nice stuff. So this has been Gauss-Jordan or Gaussian and Gauss-Jordan elimination. Thank you for watching. Hopefully it makes sense. Yeah, for more practice, do your homework. I don't know.